earlier we used to have a full-fledged convection course long back like this 40 hours. Then we compressed it into an advanced heat and mass transfer course. Some of you have taken that course, and now this has been made into an elective so that more of convective topics can be covered basically. In that, what Dr. Arvind has done so far is given you the for almost 30 hours laminar heat transfer, convective heat transfer study is incomplete without without a study of turbulent heat transfer. But turbulent heat transfer cannot be done without the knowledge of turbulent boundary layers, which cannot be done without the knowledge of turbulence per se. So this is a very unique and complex kind of a convective heat transfer compared to the laminar convective heat transfer which you have done so far. In your course on incompressible compressible flow, you have done incompressible. So boundary layer theory must have been done there. Turbulence was done. Turbulent boundary layers, was it one class system? We will try to do something about it, although the time is a little limited, but we will try to do this. But before I go into turbulent heat transfer and free convection, Dr. Arvind, I can do the Coet flow you said. Coet flow can be done. I would like to tackle one other particular problem in convective heat transfer, which is called the Coet flow. This is a very simple geometry. It is not a boundary layer flow, but it gives us tremendous amount of experience, actually exercise experience in simplifying the total overall complete Navier-Stokes equations to a very simple set of equations, and then you are able to solve it by hand in the class without necessity of any other complex solution methodologies like series solutions or transformations, numerical methods especially. You can get, with certain assumptions which are very reasonable, you can get solutions for heat transfer in a very direct, complete fashion without resort to computers or any other complex mathematical techniques. Number one. Number two, what is so great about it? Why should we do that? we have very nice codes available today. You know, you put in all these things into your code, whether a finite difference technique, finite volume or finite elements, you will get the answer. That is true. But the beauty of this particular problem, as I see it, and it's really exciting, that very important concepts in convective heat transfer, at least couple of them, 3 of them, come out of this very simple solution. So basically there are 3 reasons why this particular flow situation that I am going to do is important. One, it is considered in literature as one exact solution of the complete Navier-Stokes equations. If you please make a difference between the complete set of Navier-Stokes equations and the Prandtl's boundary layer equations. What is the difference between these two? By the way, I will be asking some questions, please respond. I do not write too much on the board, I want you to write down. What is the difference between the Navier-Stokes equations and the Prandtl's, as the name suggests, boundary layer equations? What is the boundary layer? Yeah. What is the boundary layer? What is define a boundary layer? Don't say all that. You be a little bit more firm. Yeah, you are right. So where the viscosity affects, therefore, what particular force does viscosity affect? Huh? No, you have to answer me. What force does this property of viscosity of fluid affect, control? Shear. No, you should not take so much time to answer this question, you know. So, viscosity property of the fluid, there is a force, shear force. These together, rather along with the velocity, actually give you the shear stress finally. So, there is a layer, as you said, very close to the surface, where when you say viscosity is important, it is not viscosity that is important actually, it has an effect. It is the shear force, shear stress that is important, and these shear forces are of a magnitude much higher than what it could be outside the boundary, therefore they are important. The property of the fluid which comes into picture is the viscosity. For you to have a shear force, shear stress, it is not simply viscosity that is enough. There should be a velocity, there should be a relative velocity actually. If you look at what is the fundamental expression for for viscosity, okay, defining viscosity or the shear stress equation. Give me the complete thing, say it loudly. If we make mistakes, it is okay, no problem.
Shear stress is equal to mu times gradient of the velocity.
So you must have the viscosity, there should be a gradient, it is not simply the velocity, it is a gradient. So tau equal to mu du by dy, del u by del y is the, what is this law called? Newton's law of viscosity. So it is actually a definition for viscosity in one way. So what does the Prandtl's boundary layer equation, how does it now differ from the Navier-Stokes equations? If you want, I will go back a little bit. Before Navier-Stokes equations, what kind of equations were present, were used for fluid flow? Huh? What is it? Euler's equation. So Euler's equations, now can you tell me what is the difference between Euler's equations and the Navier-Stokes equation? They look very, very similar, almost identical except for something. What is the difference between Euler's or Euler's equations and the Navier-Stokes equations? Viscous term is coming into picture in the Navy, that is a very big achievement. Find out when the Navier, why is it called Navier-Stokes equation, please find out if you have not. When was it actually proposed, please find out. I want all of you, at least I am interested, all of you to be interested in the history of these things, history of science per se. History tells you a lot. Today when I am talking about this, Dr. Arvind is talking about it, it is as if we know about it forever, it has been as a given thing. For us to come to this stage, lot of work, lot of thinking, lot of research has been expended in the last 200 years, and what we are giving today is as if it has been there forever. You should really look at how the history of fluid mechanics has developed, history of heat transfer has developed, who have contributed to all this, and what were they doing. Today the moment I talk about heat transfer, you will get an expression. What were they doing when they did not have the equation? Who developed this equation, for example? You know, I want you to please think, look into history. Today everything is available at your fingertips. So Navier-Stokes equation fundamentally was a great jump in knowledge as well as utility compared to the Euler equation. This was in the 19th century. 19th century was the time when tremendous advances were made in both in fluid mechanics, to an extent in heat transfer, but the real advances in heat transfer have been in the 20th century. Really, 1900 to 2000 has been a great period for advances in heat transfer per se. But as far as at least we are concerned, convective heat transfer, the real foundation for that was in the 19th century, starting from the Euler's equations, then the Navier-Stokes equations. What is the fundamental heat transfer equation which was developed in the 19th century, which you use it all the time, in convection also you use it? Fourier's law of heat conduction. Find out go to the original paper if you have a chance, go to the paper, Fourier, James Fourier, a French mathematician. He gave this heat conduction law. Euler's equations were there without viscous terms. Navier and Stokes, these two are different people, by the way. Find out why there were two names there. Navier is different, Stokes is different. You might have heard of the Stokes hypothesis, but you have not heard of the Navier's hypothesis. So find out why this was called so. So Navier-Stokes equations finally in the late 19th century really gave a push to the science of fluid mechanics from one particular point of view, that is consideration of the shear stresses. And only then really the aeronautics industry developed. Once this point was understood that even for air which has a very low viscosity, shear stresses could be important under certain conditions. Tau equal to mu du by dy, so you can neglect a shear stress in a flow either when du by dy is 0 or vanishing, or mu is vanishing. Air has a very low viscosity, but even though air has low viscosity, and several engineering fluids including water, low viscosity, in their flow shear stresses become important when velocity gradients become important. That is the point you should look at. Otherwise viscosity was known. They did not know how to bring this into mathematical form. What is the D'Albert's principle or D'Albert's paradox? If everything is considered as ideal, inviscid, ideal fluids, so a solid body can move through it forever without being retarded. But experimentally everybody could see it was retarded, and that was what was giving tremendous retardation, tremendous slowing down of any vehicle which moves in the air, including the automobiles, for example. So there was tremendous research that was going on at that time, and the credit for bringing in shear stress into our engineering consideration and mathematical possibilities is given to Navier-Stokes and the Fourier's law of heat conduction from the heat transfer point of view. But in 1904 something extremely important also happened. 1904, so Navier-Stokes equations were available. 1904 something else happened. What is that? Prandtl, Ludwig Prandtl. Please find out about his life. You have a book by him in the library, a green bound book. Please go and study that. Ludwig Prandtl proposed, after studying Navier-Stokes equation, after a lot of experimentation, he was the first one to propose shear stresses are very important, it is all very fine, but these are important only adjacent, in a very thin layer adjacent to a solid surface on which the fluid is flowing. This was it would now appear to be as given, but for him to come out with that physical idea, concept, and then take care of the complex Navier-Stokes equation, that was a huge achievement of those times. Now you are coming to that. So from Euler you graduated to Navier-Stokes. From Navier-Stokes I would say you graduated upwards to Prandtl's boundary layer equations, because he simplified them tremendously. He said all these complete Navier-Stokes equations need not be considered in their completeness in the layer very close to the surface. It is enough if I take certain terms, certain assumptions I can make, and then a mathematical equation I can derive, a mathematical model, the solution of which will give me the shear stress. What is the major mathematical impediment, I won't say difficulty, with Navier-Stokes equations, the complete Navier-Stokes equations? Nonlinearity. Look at the left hand side, u del u by del x, v del u by del. Nonlinearity and nonlinearity, and this is the problem with Navier-Stokes equations from a mathematical point of view. For engineers, while pure science is important, pure mathematics is important, but for engineers certain assumptions are okay, certain overall picture is okay, as long as we get engineering wise applicable solutions without bothering too much about how they originated. A scientist need not know engineering, but an engineer should know the science behind boundary layers, science behind fluid mechanics. Then you will be able to appreciate it better, but more than that you will be able to correct yourself later also. So Ludwig Prandtl simplified the Navier-Stokes equations into what now we call as Prandtl's they are referred to as Prandtl's boundary layer equations, meaning they are fully applicable in that boundary layer, which is a very thin layer next to the surface. This he made it only for the shear stress, not for the heat transfer actually, although we then extended upon it. This is one part, I will come back to this. What now we will come to the heat transfer side. What is the fundamental objective of convective heat transfer? H. Why do we want it? Why? Tell me, give me a complete answer. Yeah, that's Nusselt number is then simply a non-dimensional. What is that equation? Give me the equation. I know you know all of it. Not that you don't know. I am trying to. My first class. I am in the developing region. I want to develop by tomorrow day after into my fully developed flow conditions. Q is equal to, and what is it called? Huh? Is it really a law? That's the point now I wanted to ask you. Can you, okay, now just go back on it. What are the modes, fundamental modes or mechanisms of heat transfer? So there is, these are the leftists, these are the rightists here. They don't want, they say only conduction and radiation, they say conduction, convection, radiation. Yeah, actually convection, if you see, is a modified form of conduction basically. The ultimate mode of heat transfer right at the interface, at that first micro layer, is conduction. How do you know this mathematically? What do you do? How do you know this? No slip, okay. No, I am looking at that. So how do you connect conduction to convection with this concept? Let me put it the other way. How do you connect conduction to your heat transfer coefficient? Conduction at the wall, at the interface to the heat transfer coefficient. What is it?
Divided by delta t. Minus k dt.
So H delta t is equal to minus k dt by dy equal to 0. Now on both sides, what is the difference in the coefficients? In terms of the feature, the characteristic of the coefficients. H delta t you have k dt by dy. No, unit wise okay, but anything more than that okay. One on the right hand side dt by dy is a gradient, and on the left side it is not a gradient. Okay, number that's very clearly seen. But I want you to tell me the difference between the other two factors, the other factor on the right hand side and the left hand side.
Property of fluid.
What is property? Now you come to K is a property of the fluid, H is not. H is a function of what then? Give me the variables. That is a flow condition, yeah, geometry and the properties. Therefore, it is not a property, it is a characteristic. Now, therefore, now I am coming to this point, Q is equal to H delta T or HA delta T, we should not be strictly calling it a law. Now, come to conduction, write down the expression for conduction, Fourier's law, you know that if you want to. Q is equal to minus k dt by dy. Write down for radiation, Q is equal to sigma epsilon T14 minus T24. Write down for convection H delta T. Now look at these three expressions. For conduction, you have K, which is the thermal conductivity, which is a property. On the right hand side, for the radiation, you have epsilon, property coming into picture, and in both of these cases, of course, there is no flow. In the convection case you have Q is equal to H delta T, where there is no property alone, property is incorporated in H. While you call correctly Fourier's law of heat conduction, Stephen Boltzmann's law of radiation, it is not strictly right to call this Newton's expression as Newton's law of cooling, because it depends upon geometry, flow and the property. You might say, what is so great about it? I want you to understand the difference. You do not have to accept everything as it is said. You have to understand. Like convection is not a, in a way, not a fundamental mode of heat transfer. It is a modified form of conduction. It does not matter in your calculations, but you should understand as scientists, engineers. Similarly, Newton's law of cooling. So then, if it is not a law, what is it? It is simply a relationship. It is simply a definition of H now. Like tau is equal to mu du by dy, Newton's law of cooling. It is a law of cooling. It is a law because mu comes into picture. It is a property. Q is equal to HA delta T or H delta T flux. H is a characteristic. It is a definition of H. This was a very fundamental thing. Find out how this came up. You called it Newton's law anyway already. So, although heat transfer developed tremendously in the 18th and 19th and 20th centuries, Newton himself has contributed certain things, especially Newton's second law of motion you are going to use, Newton's law of viscosity you are going to use, and the so called Newton's law of cooling, so called I am saying. So, some of these concepts came from the time of Newton, that is in the 18th century, 17th, 18th century. There was not much of work. Then Fourier's law of heat conduction came into picture, Euler's equations came into picture, graduated to Navier-Stokes equation. Then came this seminal year of 1904 when Prandtl said, I do not have to solve the entire Navier-Stokes equations, because the engineering at that time, the engineering objective of the study was shear stress as far as the aeronautics is concerned. That was the drag coefficient that they wanted. That was the purpose. Drag coefficient cannot come from your Euler's equation. It just does not exist there. The complete Navier-Stokes equation has viscous term, so it has to be solved. Then Prandtl said, no, you do not have to solve this, let me try to simplify. Order of magnitude analysis, scale analysis. Finally, he gave those, even though they are nonlinear still, they are much less formidable than the Navier-Stokes equations. U del u by del x plus v del u by del y equal to nu del square by del y square minus 1 by rho dp by dx. So many terms, mathematical terms he cancelled out with certain argument, assumptions, some very right, some approximately right. But his intent was, can I handle the Navier-Stokes equation in a much simpler way for me to get my skin friction coefficient. That was only from the fluid mechanics part of view. Then came, of course, much later the energy equation. The same concept of boundary layer for viscosity and shear stress was extended to the energy equation to then term a thermal boundary layer. They simply surmised, as viscosity is important in a very thin layer, maybe K is important only in a very thin layer, although these two may not be equal, but they just like a hydrodynamic is not a nice word, hydro is water actually. So it is a aerodynamic boundary layer, fluid better would be a fluid mechanical boundary layer, fluid dynamic boundary layer. Like that there is a thermal boundary layer. These two concepts which came only in the 20th century. 1904 Prandtl's he presented it in an international conference, nobody bothered about it, nobody bothered. Till 1934 in one of the international conferences there were 6 papers on boundary layers. 1945 there were 280 papers, and by 2000 there is no year in which there is less than 1000 papers on boundary layer theory. That is the import, the significance, the importance, I would even say greatness of this particular concept, which we today talk as if I came up with this concept. I tell you this exists, I have never seen it. We have done experiments, that is a different matter. So 1904 is already 110 years old. Along with him, his contemporary was Nusselt. Nusselt, now you know, he he is remembered with his, he died only in 1950s, Nusselt number. I am now going one step ahead. That heat transfer coefficient, which is whose definition is given by the Newton's law of cooling, was given a non-dimensional form by Nusselt in 1925. He said he came through non-dimensional, he did not know about the Buckingham pi theorem at that time, he simply made a scale analysis. He found this group hx by k was non-dimensional, and then he said I should be able to relate it. By that time Reynolds number was already, when did the Reynolds number, when was it proposed? Reynolds number? Fine, Osborne Reynolds 1883. That is another major experiment by Reynolds experiment. Please look into Reynolds experiment, where he injected a colored dye into a pipe flow under extremely low velocity conditions, and you could see a very nice, as now we call a laminar filament of a layer, and then when he increased the flow he started seeing fluctuations. He said, what is happening? The velocity at every point is changing with time and space. That is how the idea of turbulence was actually visualized, and then that particular parameter over a period of time it was given the name Reynolds number. What does Reynolds number signify? What does it physically signify? Inertia by viscous forces. So as you increase inertia is your u del u by del x actually. You please make it out. Reynolds number is inertia by viscous. So rho u du by dx divided by mu d square u by dx square. If you do that, you will just get rho v d by mu, that is v d by nu, v being a characteristic velocity. Prandtl did another thing. I mean, he did not do it per se, but when he non-dimensionalized, I mean he made a scale analysis, he got this term mu by alpha, actually mu Cp by k. That is called the Prandtl number today. Now you see, over a period of time, from the fluid mechanics point of view, 1883 Reynolds turbulent, laminar turbulent transition came into picture, and a number, Reynolds number, came into existence. Then Prandtl gave the Baudelaire theory in 1904. Prandtl talked about Nusselt around 1925. Prandtl, by the way, Prandtl did another thing in 1925. We have not yet gone to turbulent Baudelaires, but I will tell you now. He developed the first, what we call the zero order model for turbulent flow, called the Prandtl's mixing length theory. Please note down, we will talk about it later. So Nusselt then gave us the non-dimensional form of Higgs. There is nothing more to it. We can talk about convection by conduction. We can then improve, give physical significances. They have physical significance. So over a period of time, you finally got convective heat transfer to be represented by Nusselt as a function of Reynolds and Prandtl. Nusselt is a non-dimensional form of the heat transfer coefficient, which came from Newton's so-called law of cooling. Reynolds number from Reynolds, because of the laminar, that number differentiates between laminar and turbulent flows. And then Prandtl number. What does Prandtl number signify? When I give you a Prandtl number, what would you, what information will you get? Fluid properties, yeah. Type of? Yeah. It identifies the fluid. That is the thing. Yeah, it's fluid properties. Therefore, it identifies the fluid. There is no, you can't miss anything. If you say Prandtl number is equal to 0.72, it is air and most of the gases. Somebody need not tell you, find out whether it is a oil or a liquid metal or water. No, it is gas, end of the matter. On the other hand, if I say this Prandtl number of this fluid is 0.01, you know it is a liquid metal. Mu Cp by k, k is extremely high. On the other hand, if I say the Prandtl number is some 1000 to 50,000 mu Cp by k, where k and mu are varying with temperature, and that has to be oils. So you have oils, light oils, heavy oils. So the moment, that is the beauty of this particular number. Reynolds number gives you the type of flow. Nusselt number gives you the non-dimensional heat transfer coefficient, which is hd by k. No, you can write it as h over k by d. So it is a convective heat transfer coefficient divided by the conduction part. It is a relation between these two. And then Prandtl number signifies the fluid. This is extremely important. So, if you look at this general expression Nusselt as a function of Reynolds-Prandtl, you have everything coming into picture here. Left hand side is what we want, that is the objective of convective heat transfer study, getting, you said Nusselt number in the beginning, getting the heat transfer coefficient in the form of a non-dimensional number, but this is a function of the flow, the geometry and the properties. Flow and the geometry property come through the Reynolds number, it will tell you it is laminar or turbulent, and the Prandtl number says this is the fluid. You cannot therefore use, this is what I tell a lot of students. So, do not think the equations are available in the some tables. So, why should I attend my class? I can simply take any equation, you will get all equations in force convection and Nusselt is a function of Reynolds and Prandtl. But you should know what is the background of this, what is the significance of all this, how does H, which is our major goal in convection, how does it vary with flow, that is the velocity, the geometry and the properties of the fluid. So, the engineering objectives are two in convection heat transfer, actually it is not one, we should say it is two, because you have to get the skin friction also. That is a purely fluid mechanical thing, but when we are talking about convective heat transfer, skin friction coefficient determination is important and heat transfer coefficient determination is important. When do you think viscosity, or do you think viscosity will affect the heat transfer or not? Viscosity is a purely fluid property. Heat transfer coefficient is a function of the property. These two are the objectives. Do they interrelate? Do they affect each other? That affects the whole process. Do they affect each other? How does heat transfer affect fluid flow? Now, mu is a function of temperature, not so much of pressure. Rho is a function of pressure and temperature. So, heat transfer, this is very important. Therefore, we talk about low temperature heat transfer, high temperature heat transfer and the effect of properties which are a function of pressure. Properties are a function of pressure and temperature. So, we should look at the pressure and temperature, how do they affect the properties, whether they will affect my skin friction. On the other hand, how about friction, viscosity affecting heat transfer coefficient?
Resisting heat transfer. Resisting heat transfer forming boundary.
What is it?
Resisting heat transfer.
Resisting. That is a new term, maybe we mean the same, but I am not able to get the.
Because local temperature because of heat release and then that will affect the heat transfer line.
Yeah.
Viscosity affects the flow.
Viscosity affects the flow. Okay. Yeah, this is like in all our the same thing, we look at different angles. So, you should give me different angles to this. Viscosity causes friction. I was looking at from the friction generates heat. Sometimes it is negligible, most of the time we want it to be negligible, but not all the time. When frictional heat is not negligible, it affects your temperature profiles. This effect is called the effect of viscous dissipation. So, actually you should where it is mathematically already there in your energy equation, do you remember? U del u by del x plus v del u, rather u del t by del x plus v del t by del y is equal to alpha del square t by del y square, simplest of the boundary layer equations, plus q triple prime by rho Cp if you have the heat generation, and the last term is what? Mu phi. Phi is a dissipative. Most of the time we neglect it, we say you are causing a lot of problems, so let me not bother you. But imagine if that is important, your whole energy equation is affected by that. Again, it is not simply the viscosity along with the velocity gradients, that phi is nothing but all velocity gradients, as you will see. So, they are all mutually affecting each other. So, it is possible in certain conditions we consider, sometimes we do not. Then as scientists we should say, when do you consider viscous dissipation, when we do not. That is from viscous dissipation point of view. Now, if you come to the flow itself, you know, laminar, turbulent, we talk about this, but there is an in between zone, the transition zone actually. Laminar, what is the turbulent What is the critical Reynolds number for flat plate? Huh? Huh? For flat plate? 5 into? For pipe? So when you say 5 into 10 to the power 5, where you got it from Bhagavad Gita, is it? Where did you get it from? One beautiful value. Actually, if we go a little bit detail, there is a transition zone. So there is a initial Reynolds critical Reynolds number and a complete critical number. It depends upon so many things, including the surface, type of surface, obviously. So it's not that suddenly the flow, which has been very nice, well behaved, it jumps to turbulent flow. It happens over a Reynolds number range. So initial Reynolds number in our general handling of convection, we may not bother much about it, but you should know that there is a range and it can be controlled. In fact, a whole lot of things can be controlled by controlling the flow. That is possibly, in some ways it is in your control, and especially also controlling turbulence itself and the transition to turbulence. So if you know some of these fundamentals, you would like, instead of simply accepting whatever there is, shear stress or heat transfer coefficient, you may say, can I control this? Can I control the flow for whatever reason? Can I control the heat exchange process? Within certain limits, you can do it. That is why you should try to go as deep into the fundamentals as possible. As an engineer, finally an actual technical person may not bother about these things, but he knows. If you go to a person who is handling a heat exchanger in industry, he knows how to increase the heat transfer rate, how to decrease. He may not know the basis of that. Sometimes he increases the flow, he is actually increasing the Reynolds number basically. There are many ways of controlling heat transfer, and if you know that Reynolds number of the flow, from the flow point of view, controls heat transfer in a given heat exchanger, you can do something with the velocity, you can do something with the type of the surface. That is the reason why I would like you to, Dr. Arvind has done a lot of thing on a flat plate and pipe. I am just adding to that. If he has not done that, please read about the history and try to get a picture of where we are today, why we want to study convective, what has been the background. That will give a little bit more, I would think, excitement, understanding of the whole process. Otherwise it will become a little dry. I will again talk about similar things. I want you to drawing a convection chart. A convection chart. You must be able to do it on your own. I will just guide you on that. I like this particular thing. I always emphasize for us to get a full picture, especially for beginners. I know you have already done quite a bit of convection, but still I want to do this. On the right is a chart or a sequence of events, let me say. On the right hand extreme you write the purpose of convective study. And I want you to write, what is it? Determination of, I want you to write this. No, I want to write purpose of convection study is what? Determination of H. Write down that. Then go one step ahead, put an arrow there. How do you get this H in our scientific approach? What do you need to get that H, model wise or experiment wise? Temperature difference, no. You have done all this. I am actually asking you to put whatever you have done in this chart fashion or a table fashion. How do you get H actually from your analysis? What is it that you use, what expression for you to get H from all the analysis? Laminar itself, what all you have done? Yeah. What? Tell me what? Fourier's law? At the surface, no, this is what I wanted. At the surface, you apply the Fourier's law, write down. So, Fourier's law comes into picture. Minus k dt by dy at y equal to 0 equal to, isn't it? That is how we are going to get it. That is the second what box in my chart. Where do you get the dt by dy at y equal to 0? You should always say dt by dy at y equal to 0, it is at the wall. We are looking at convection, heat transfer between a solid surface and a flowing fluid. For me, 3 conditions are to be satisfied in convection. Can you tell me what? We are talking about a solid surface and a fluid. Okay. I want 3 conditions for me to say this is convective heat transfer. Conditions is a very big word, situation, but I would like to use the word condition. There is a solid surface, there is a fluid. When do we talk about convective heat transfer? Huh? Huh? Maybe I have not. Huh? Motion? Relative motion. That is very important. But before that, something else. Correct. Relative motion is one of the conditions for me. Temperature gradient, temperature difference. 2. The third one, I am saying purposely convection. It is very simple. You will say, oh, sir, we know about it, but that does not matter. Can convection occur if the surface is here and the fluid is flowing here? There should be contact. This is what we are talking about. So, convective heat transfer is that type of heat transfer which occurs when a fluid and a solid surface are in contact with each other, number 1. There is a relative velocity and there is a temperature difference. All the 3 must be. Why I am saying this? If a solid surface and a flow of different temperatures are not in contact with each other, also there is heat transfer occurring. But what is that heat transfer? It will be radiation. And if the fluid is in contact with the surface, there is a temperature difference, but there is no fluid motion, even then heat transfer occurs. What is that heat transfer? Huh? So, conduction can occur, radiation can occur between a solid surface and a fluid, depending upon whether in contact, no motion, no contact, no motion, but convection is contact and motion.
In natural convection there is no motion.
Motion is created by the temperature difference. Motion is created by nature. Nature, here we are talking about the G effect actually, but it is better sometimes to call it free convection, other thing. But you are perfectly correct. What you can talk about is in forced convection, there is an imposed flow. A flow is forced by some means. In free convection, that flow is created inherently within the fluid itself because of the existing temperature difference. So, it is a good point. That means, I mean, we know that for heat transfer, first of all, temperature difference must be there. Of course, there is. If these two are in thermal equilibrium, there is no heat transfer. So, that is a. But your point is well taken. We will emphasize that. So, convection is that mode of heat transfer between a solid surface and a fluid when they are in contact, when there is a relative motion, and when there is a. Why I emphasize this is the following. Let us say there is a contact between the solid surface and the fluid. There is a temperature difference, but if they are moving together at the same velocity, there is heat transfer, but that is by conduction only. There is no relative motion, there is no boundary layer there. So, conduction can occur in a fluid, I mean between a solid surface and a fluid when they are static, both of them, or both of them are moving at the same velocity. That is why I bring in the term relative motion must be there. Even if there is a 0.1 centimeters per second difference, we say there is a relative motion. But then you can also see the heat transfer due to the fluid motion is very mild, it is not that much in terms of Reynolds number. So, that is my as you students say take on convection. Is it convection only between solid surface and a fluid under these conditions? Do we have to stress on solid surface? It could be heat transfer, it could be mass transfer. And my point here is that it is not necessary that we always talk about a solid surface. Now, now there is a big water shortage in this city and we are going to feel it. You know why? One of the reasons for water shortage, of course there is no rain, but if you go to any of our reservoirs, they are all open surfaces of water. You think there is nothing happening there at the surface? There is a wind blowing. In fact, at 1 o'clock the wind sets in, the sea breeze sets in, and there is a wind flow over these surfaces. What is happening at that time? Evaporation. There is a mass transfer. So when there is a concentration difference, there is a mass transfer. That we call it as a convective mass transfer. So there is a concentration bound layer, and similarly, if there is a temperature difference between these two, heat transfer will occur. And sometimes you can have isolated cases of isolated heat transfer, mass transfer, but there are cases where both of these are possible, heat transfer, mass transfer simultaneously. But in convection, fundamental to heat transfer and mass transfer is the fluid motion. Fluid motion plus conduction, Fourier's heat law of conduction, is your convective heat transfer. Fluid motion plus Fick's law, that is your mass transfer, convective mass transfer. So I would also therefore like to say convection is not necessarily between a solid surface, although we focus on that, between two fluids, as long as there is contact, temperature difference, fluid motion, relative velocity is another point I wanted to make. Now if this flow is from an external energy, that is forced convection and free convection, there are mixed convection cases also. To get a handle on quantitative handle on heat transfer coefficients and skin friction, we do two things: either we follow a science model or a engineering model. Heat transfers as a subject has two aspects, science and engineering. Engineering means you do actually experiments, so you get the heat transfer coefficient or whatever you want, measure temperatures, everything. But even basis for those experiments is your actually theory part of it. So when you talk of getting the heat transfer coefficient theoretically, you develop a theoretical model. I want you to from this come to that point, that chart. So heat transfer coefficient you get by equating minus k dt by dy at y equal to 0. Y equal to 0 is very important. Y equal to 0 is the interface, is equal to h delta t, Tw minus T infinity. Now go to the next box. What do you have to get in this equation? What is it that you have to get? Temperature. No, first you should say, I want you to say you want the temperature gradient at the wall. You do not really care about the rest of the thing. I want dt by dy at y equal to 0. This is very important for me. dt by dy is there from y equal to 0 to y equal to delta, but I do not bother. dt by dy at y equal to 0, wall gradient. Now you go to the next. How do you get the wall gradient at y equal to 0? Only this is what is making all your convection a big issue, to use a very mild word. All you need is dt by dy at y equal to 0. Therefore, when you do experiments, ladies and gentlemen, you do not have to measure the entire temperature profile for you to get the heat transfer coefficient. Just close to the surface is enough actually. You do not have to go for the entire boundary layer thickness. So, but mathematical, that is from a theoretical point of view, for you to get dt by dy equal to 0, you have to get t as a function of y. That means now you have determined the temperature profile. Now how do you get the temperature profile? Now we are talking about the boundary layer. How do you get the temperature profile? Go to the next box. What is the next point? How do you get the solving? You cannot simply say energy equation. Energy equation is not enough by itself. For you to solve the energy equation, you also have to solve the why. What is there in the energy equation which makes you so? Here you have u. That is the difference between your conduction equation, which is the energy equation, and this equation. Fluid flow affects your energy equation. So u del t by del x, v del t by del y. For you to get this, you have to solve the momentum equations. And momentum equation you cannot solve it on their own, you have to solve the continuity equation. So, when you solve the continuity and the momentum equations, you will get the velocity profiles. When you take those velocity profiles and put it into the energy equation, you get the temperature profile. When you get the entire temperature profile, you just take the dt by dy at y equal to 0, multiply it by k, equate it to h delta t, then you will get h. Now, from where do you get that profile? Which equations? Now you have to get the profile. So, from where do you get the equation? You have to solve the Prandtl. I want answers that I want. Prandtl's boundary layer equations you have to solve, not Navier-Stokes equations. That is what I am coming to. At this point, you have to solve the Prandtl's boundary layer equations. The entire thing, momentum equation, energy equation of continuity. It is understood that you have to do that. So, these are already simplified. Where do you get? How do you get the Prandtl's boundary layer equations? From where? From the, so write down Navier-Stokes. So, simplification of Navier-Stokes gives you the, all this you have done. I am just putting it in a certain form which I like. Where do you get the Navier-Stokes equations from? What is the basis of the Navier-Stokes equation? Newton's second law. I want start from the beginning. I say first equation, first continuity equation, law of conservation of mass. Then next three equations. Yeah, okay, I will leave it at that. Three equations, and then the last one, law of, from where does the law of conservation of energy come? Which law? First law of thermodynamics. Of course, if you are looking at mass transfer, you also add this specious equation. We will further present. On what physics do these equations depend on? I am trying to get you related this H that you want to engineering wise require to nature basically. Now look at these laws you are talking about. First law of thermodynamics. Second law also you should say, second law is important, minus k dt by dy is second law of thermodynamics expression actually. And then all the velocities come from the momentum. So law of conservation of mass. Now look at who developed this, when were these developed, what is the proof of this? Law of conservation of mass, you write down, immediately mass cannot be destroyed, created, you say. Newton has done tremendous, Newton was a really great scientist. He has done work in optics, heat transfer, fluid mechanics. Actually he was a philosopher who was looking at the celestial bodies. He started developing equations for the motion of celestial bodies, although he was just a banker. He was in charge of the treasury of England actually at that time. So he came out with these equations which happened for us to be applicable to fluids also on the earth, and then Prandtl made it to the boundary layer. And thermodynamics. Now where is the proof of the first law of thermodynamics? I am talking about a theoretical proof. Where is the theoretical proof of the second law of thermodynamics? Now you see, in science we always say any model, any law must have experimental validation. Now these are all called natural laws because nature itself is a proof for this. On the other way we say, in nature we have not found anything against this. People have tried to prove the second law of thermodynamics actually theoretically, but they got stuck. What is the purpose of this? For me, this connects, I want to connect the engineering aspect and nature finally. Finally we are dependent upon this nature in terms of the laws of nature. It is not that one man came out with these laws, whereas you have a Fourier's law of heat conduction. You have so called Newton's law of cooling, Newton's law of viscosity, Stefan Boltzmann's, but here you do not get any one name, so and so's first law of thermodynamics. It has evolved over years from the 17th century, and really find out when the first law of thermodynamics was given a mathematical representation, try to find out on your own. Now in most of the classes what we do, without telling you this, we start, let us look at the law of conservation mass and then derive. I am trying to tell you the reverse of it. You want H and you want also tau W, by the way, shear stress. So the same thing you can relate, tau equal to mu del u by del y, but you want the shear stress at the wall, tau w equal to mu del u by del y at y equal to 0. Never forget that at y equal to 0 point for convection. That du by dy I get from the velocity profile. Now you see, velocity profile you have to get from your momentum and the continuum equation for shear stress, that is the end of the matter as far as fluid mechanics is concerned. But if you think heat transfer can be obtained without recourse to this, it is not possible, because your energy equation contains u and v. So a natural law, by the way, this first law, second law, Newton's law, these are called general laws, physical laws, general laws, universal laws. They will never be disputed anywhere. But your Fourier's law, Stephen Boltzmann's, and Newton's law of viscosity, these three are not general laws. Why? Tell me. Just look at the equation and you can make out. Tau w equal to mu del u by del y, q is equal to minus k dt by dy, q is equal to sigma epsilon 1 to 4. What is common in all these three equations? Common in terms of the nature of the equation. There is a property. The moment you say property, there is a medium coming into picture. So these are medium oriented, medium based, medium controlled equations, though they are called particular laws. So we have particular laws, general, universal, natural or physical laws. From a combination of these laws now, combination of these laws lead you to the equations, which we would refer to with along with the boundary conditions, the mathematical model. So from the physical model, where you take a control volume, that is exactly what you are doing at control volume or a system, apply these general laws, you come down to very broad equations. They are not enough for you to get heat transfer. They will give you only the profiles. For you to get the heat transfer coefficient, you have to come out with a particular law, which is minus k dt by dy. For you to get the mass transfer, you should have a fixed law. For you to have the shear stress, you must have Newton's law of viscosity. So a combination of general laws based on nature and particular laws based on people's, they have developed it. Please read Fourier's law of heat convection, it's very nice paper, it is in French, some English translations are available. Now you and I take it to be so simple, q is equal to minus k dt by, what is there? Please look at that particular 1829 or so. It gives you tremendous information on what was his thinking at that time. When you put all of these things together, ladies and gentlemen, we can then say we are ready to find out, rather determine engineering wise heat transfer coefficient and the shear stress. I will end now.